Hi, everyone. Thanks for coming to our session today. I'm sure everyone's had a long day of attending different sessions, so hopefully everyone still feels energized and has had a great week so far. We'll be talking about a data platform migration journey we did at HP, from starting with AWS Redshift and then transitioning to Databricks Lakehouse. Let's start with a quick poll. Raise your hand if you've gone through or are planning a similar migration. Okay, just a couple. Fantastic. For those of you who have already done a migration, let's compare experiences after this talk. For those of you who are planning a similar migration, we'll give you an overview of our journey today. During this session, we'll give an overview of our platform before the migration, then we'll dive deeper into details we discovered, and then we'll close with some results after the migration was completed. We'll throw a lot of information at you as we walk through our migration journey, so you can always refer back to these slides for a second look. I'm Isaac, this is Kavya. We're both lead data engineers at HP. We work for HP's central data platform organization. Our platform ingests data from millions of consumer and enterprise devices. We receive data from approximately 110 million printers, 35 million applications, 18 million PCs. These devices and applications, they send data in real time. Using this data, we build central foundational data products for shared leverage. These data products might be pre-joined, aggregated, optimized for analytics, and more. We have data products as old as 10 years. Many of the platform decisions made then have had room to be modernized and improved with today's technology, especially with more and more teams around HP requesting access to the data that we store. We partner with many internal HP teams coming from various business units around the company who use this data for troubleshooting hardware and software, forecasting supply chain requirements, executive dashboards for market share, make market decisions for new products, and many other use cases. Generally here, we follow ETL patterns with some ELT for analytics-ready data products. We use Databricks Spark ETL for ingestion and data normalization, and before the migration, we used AWS Redshift as a primary consumption layer. To show a high-level data flow pre-migration, we receive consented data from printers, apps, and PCs, which land as a raw format in an S3 bucket. This data is then cleansed and turned into a semi-raw bronze data lake. This cleansing is done via Databricks. The data is then copied into a shared Redshift warehouse, where it's transformed into an analytics-ready silver product. Business teams can use this data directly for business intelligence, analytics, or build gold data products themselves. BI tools and dashboards, they can be pointed directly at Redshift, but there might also be another round of copying data back into S3 for machine learning and AI use cases using Databricks. Another detail to add, Redshift warehouses were typically provisioned one per business unit and then shared with all users. This resulted in some scaling problems and resource contention, causing problems like balancing compute resources between scheduled ETL jobs and ad hoc analyst queries. As an example, sometimes a poorly written query can take over compute resources for that cluster and then create bottlenecks for other users or other ETL processes. So as a quick summary, we already used Databricks for initial ingestion and some ML AI use cases, which are both the beginning and the end of the data flow. Semi-raw data is copied into the Redshift warehouse regularly for silver transformations. Data may also be copied out of Redshift into S3 for some Databricks ML AI work. And then Redshift warehouses, they grew in size and cost over the years, which caused issues with scaling.
So as we realized the pain points with our architecture, we started looking around for alternatives to the Redshift warehouse. Databricks SQL came up as a good option for us, but to make an informed decision, we had to really understand the similarities and differences between these two offerings and understand how they applied to HP's use cases. So we went ahead and did a platform analysis. As Isaac explained, with our old architecture, we had to copy data from our bronze S3 lakes into Redshift in order to create silver data products. And in some cases, we even moved them back into S3 to enable ML and AI use cases. The Lakehouse gives us one platform that meets all of our ingestion, analytics, and AI needs, removing the need for this constant movement of data. Redshift has strong coupling between storage and compute. This means that producers and consumers of data products have to be on the same warehouse in order to allow data to be easily shared. Redshift's data sharing solution has limitations that were just not meeting our needs. And this ties back to why we had a large warehouse that is being shared across hundreds of users per BU. On the other hand, in the Databricks Lakehouse, storage and compute are fully isolated. And this can enable us to instantiate separate compute for each team without having to worry about how to share data between them. The shared compute on Redshift became a pain point for us. One badly written query could bring hundreds of users down to a halt, and solutions like Redshift's Workload Manager was resulting in important production jobs taking precedence over users' ad hocs, which are still equally important for the business. With serverless SQL warehouses, the spin-up time is quick and no state is lost when the warehouse is turned off. And so being able to create this separate compute per team means that teams won't face any resource contention issues any longer, and we can also track costs easily by allocating them per team, per warehouse. We had pre-purchased reserve instances on Redshift to save on costs, but as any organization faces, with constantly increasing data volumes and more users being onboarded, we reached a tipping point, and we had to add on-demand nodes on and off to be able to run large production jobs. Moving to serverless SQL warehouses on Databricks could remove this problem for us. Each team can scale their compute based on their own needs, and we won't be restricted by reserved instances anymore. As data engineers, we all run into situations where builds get delayed due to things out of our control, data quality issues, upstream data availability, and so on. Having the option to scale up compute and speed up our runs to still meet SLAs can help us feel a lot more in control. When it comes to the user experience side of things, Redshift only provides us with very high-level query plans and metrics. So if I had a query running for days together, we could not tell, is the query progressing along? Are we still reading in the data, or are we just about to write out the data? How do I improve this query? It's all very black box. The query profile and the Spark UI in Databricks SQL can be game changers in this regard. They're very actionable. We can correlate lines of SQL code to stages in the query plan. And the metrics given per stage can help us identify bottlenecks, track progress, and be more informed of what is going on. When it comes to the SQL capabilities, with Redshift, we have very traditional SQL capabilities. The Lakehouse expands on top of these with a richer function set, including map functions, Lambda functions, and now even AI functions, all enabling modern analytics. Our Redshift warehouses have been around for 10 plus years. Users are very comfortable and familiar with the technology, and we have well-established integrations with different BI tools. As with every new platform, there comes associated a steep learning curve that users have to scale, and this migration is no different. As we go over our migration journey, you'll see how we leverage the strengths of the Lakehouse to improve our data platform and overcome the pain points that we were feeling. Quickly looking back to the pre-migration data flow, just want to highlight the movement of data that we were referring to between the S3 lakes and the Redshift warehouses. With this migration, we swapped out this Redshift warehouse layer with Databricks SQL warehouses. So post-migration, this is what our end-to-end architecture looked like. All of our processing is now happening within the Databricks environment, starting from ingestion all the way till analytics and ML and AI.
To show our high-level migration plan from starting with Redshift and then transitioning to the Lakehouse, we first start with platform analysis, which Kavya covered in the previous slides. There were aspects of both technical benefits and cost analysis, which I'm sure everyone here is familiar with, to convince your management it's a good idea to do a migration like this. In our platform, we host both platform-owned foundational data products and partner-owned data products. We duplicate these in the Lakehouse environment so that we can easily compare them between the two systems and make sure that the data is equivalent. Once we're confident in these data products, we can deprecate the Redshift versions and eventually sunset the Redshift instance. This gives a period of transition for the end users and helps us scale down the Redshift instance as more and more end users move away from it. It helped us stagger the move of end users off of Redshift so that we can work with partners one by one on their use cases and slowly scale down the usage of Redshift. This does result in a period of maintaining both Redshift and Lakehouse resources and costs, but it gave a much smoother transition for our partners. Our platform consists of many data products. This is a simplified example of one data product architecture that was migrated. Within Redshift here, we use dbt to execute many of our ELT processes. Bronze data or semi-raw data sets, it's first copied into Redshift. From there, we have models that might perform joins to enrichment data sets, for example, and then create data marts. Data might need to be copied again outside to S3 for ML AI use cases with Databricks, but we can connect BI tools like Looker, Power BI, and ThoughtSpot directly to Redshift. Ad hoc queries can also be run from Redshift. And lastly, business data products, they can be built from the Redshift products using dbt or LookML. Post-migration dbt architecture, it stays mostly the same, which simplified the migration for so many data products that our organization hosts and maintains. We don't need a separate step to copy our semi-raw bronze data sets into an external warehouse because that data is already within Databricks. We can still use dbt executed within Databricks, and we don't have to copy data out in order to use Databricks ML AI. BI tools, ad hoc queries, and business data products, they can still be created using Databricks SQL warehouses or even other Databricks tools. Existing dashboards on BI tools, they can be configured to point at Databricks SQL warehouses with pretty minimal changes required.
So now that you have a background on the what and the why behind the migration, let's take a look at the how. So how did we go about doing this migration? We faced a lot of challenges and had a lot of learnings through this process that we would like to share with you all today. So we broke down the migration for each project into logical chunks and developed timelines around them in order to help with cross-team collaboration and budgeting. So every migration started with needing their upstream data dependencies available in the Lakehouse. For us, since our ingestion was already happening into S3 data lakes, we only had to set up the correct access control around them to be able to use these bronze data products. In some cases further downstream, we made static copies of our Redshift data sets available in Unity Catalog to unblock teams. We then moved on to setting up resources for every project. This included Unity catalogs, SQL warehouses, service principals, and so on for developers to start testing with. Alongside this, our platform operations team was setting up automation to manage all of this infrastructure as code using Terraform. Since we have dbt projects, we had to migrate from the dbt Redshift adapter to start using the dbt Databricks adapter, which mostly involved configuration changes. But along with this, there was a SQL migration to convert Redshift SQL to Databricks SQL. While the syntax is quite similar, there are some nuances and gotchas that we'll dive into in the next section. Post-code migration, we moved on to dev testing and validation. With these small dev data sets, we focus on doing full deep compares with our Redshift results to ensure correctness before moving on to expensive production testing. Once we got good results on dev, came the production testing, which revealed issues with scaling and eventually uncovered some bad queries. In these situations, we had to go back to the whiteboard and come up with new solutions to leverage the strengths of Spark. Following this was thorough validation of the data products not only for us to gain validation in the new code, to gain confidence in the new code, but also for our partners to trust the new data product. We use data from Redshift as our source of truth and verify the new results. Once the consumers started using the data, we use their feedback to optimize the data products to meet their needs better. We use methods like liquid clustering, predictive optimization, and data skipping stats collection to tune the data products to suit their needs.
I wanted to highlight a few examples of SQL syntax differences between Redshift SQL and Databricks SQL. These were usually discovered during the data product migration development. These two functions here, bitwise operator and system date, require a different function, shift left and current timestamp in Databricks SQL. These are examples of functions that will error out if ran in Databricks because the functions, they don't exist. In this next example here, for integer division, Redshift uses the slash operator that returns an integer. In this example, 5 divided by 2 returns 2. Databricks slash operator, on the other hand, returns a float. For the same functionality, we have to use the div operator. Using the slash returns 2.5, using the div operator returns 2. Some of the same functions or operators like this can return different results, which makes it hard to debug. The last function here is an interesting example where the same function exists in Redshift and Databricks SQL flavors. This is a simple dateDiff function returning difference between two dates. We use this function really heavily in data products for window functions and aggregations. In this example, the two dates we're comparing is the last day of 2008 and the first day of 2009. Redshift's behavior is to consider the unit of the dateDiff function, in this case year, and return the difference of that unit. In this example, the difference between the years is 2009 minus 2008, so the function returns 1. The same function in Databricks returns the difference of the two timestamps themselves and then rounds to the unit. The same function returns 0 because there's only 1 day of difference between the dates. 1 day rounded to a year results in 0. Overall, it's important to debug and understand the differences in SQL syntax. Otherwise, it's easy to make mistakes when migrating a lot of code. Small differences like this can cascade downstream and accidentally affect forecasts or other precise calculations. Another example of SQL syntax differences is lateral column aliasing. Redshift is more lax about this. In this select statement here, we're creating a column B and then directly referencing it in the where condition here, all within the same statement. This statement, it works in Redshift. But running the same select statement will error out in Databricks because Databricks doesn't see that column B exists yet. The workaround is to create an extra common table expression, or CTE, creating column B first, before referencing it in a subsequent select statement. We had used this feature, lateral column aliasing, in Redshift SQL for years, unknowingly. It caused a lot of code changes during our migration to find this out. When we discovered this, Databricks team, they were really helpful in helping us debug and test fixes in private previews. This behavior was actually even more constrained before, but we worked together with the Databricks team to improve lateral column aliasing.
This migration was a good opportunity for us to rethink design choices. One of our SQL models written more than 10 years ago was a complex monolithic SQL query transforming and writing about 60 billion records. Given this was an atomic operation, any failure meant that the entire query had to be rerun, losing precious minutes and dollars. Moving to the Lakehouse allowed us to leverage structured streaming to turn this into a fault-tolerant process. We now have access to many configuration options and can make runs go faster if needed. The checkpoints that are created as part of the streaming allow us to pause and resume the jobs whenever needed without losing progress. And we were able to achieve this while maintaining comparable runtimes and costs. While trying to scale various pipelines across different stacks, we can make use of the SQL query profile provided by Databricks to help determine warehouse sizing. Metrics like the spill to disk give us a good indication of when to change the warehouse size. And on average, we were observing good performance to cost ratios as we changed warehouse sizes, which helped make our warehouse sizing decisions easier. Another place that the query profile has helped us was with discovering pitfalls in our code. In one such situation, we had a query that took almost 9 hours to run on 14 nodes of RE316XL on Redshift, which is a very large warehouse, and we could never figure out why it was so slow. When we tried to run this on a 3XL Databricks SQL warehouse, it just seemed to be struggling. There was a lot of spill to disk, and the live query plan showed us that the query was not really progressing. When we investigated the query profile in the Spark UI, we noticed that all of the data was being processed by a single Spark node very early on in the process. You'll also see that the query plan over here is a bunch of tasks that are set up to run serially one after the other, and that there's not much parallelization in the query plan. This was a red flag for us. Using the visual query plan, we were able to narrow down the cost to a single window function, which turned out to be a partitionless window function. So this window function was forcing all of the data to be processed in one single Spark node, and other stages could not be run in parallel. And all this window function is doing is calculating the maximum value of a timestamp, just in a very inefficient way. And so once we figured this out, the fix was simple. We just swapped out the window function for a regular aggregation and noticed an immediate improvement. The query completed in under 3.5 hours on the same 3XL warehouse. Looking at the Spark UI, we could see the task is now being shared across nodes, just like it was meant to be, and the query plan also looked a lot more parallelized. You'll see that the new query plan shows a lot more branching early on in the process. This is a zoomed in view of the initial part of the query, compared to the old plan where not many tasks are being run in parallel. So having access to this rich set of metrics from the Databricks SQL warehouse means that analysts and developers now feel empowered to understand how their queries are being processed, debug and improve their queries using quality metrics, and just not feel like the database is a black box.
A few slides ago, we talked about replicating data products in both Redshift and the Lakehouse. When migrating data pipelines between two different platforms, pipeline logic needs to be translated, which can introduce a lot of new bugs. Different strategies are possible to do manually, like spot checks on primary keys or testing translated logic individually, but that's not really a scalable solution, especially for tables that contain 100 million rows or more. We worked together with the Databricks team to build an automated notebook that first pulls data from Redshift as a data frame and then compares it against the Lakehouse data frame. It starts with hashing each row from Redshift and the Lakehouse, and then joins on the primary keys so that we can compare the rows that don't match. This helps us isolate rows to debug. The notebook can also interleave columns between Redshift and Lakehouse into a single data frame so that we can compare values side by side. The comparison does type checks and has configuration for float precision forgiveness for a specified number of decimals, so that helps considering floats with 8 decimals to be equivalent, for example. This is a dashboard output of the notebook. We can configure the notebook to run as a job. We can filter data to be a certain time window that we want to compare. Over here on the right side, there's some metrics about number of Databricks rows, number of Redshift rows, and then the differences between them. There's a graphical representation on the left so that we can see it really quickly, and then there's a tabular view with more details below. Overall, these A/B comparisons, they helped us discover some upstream data differences, as well as SQL functionality between Redshift and Databricks SQL. For example, we talked about that division operator that looks the same but performs differently. This type of validation helps us discover those differences. It also had the benefit of giving confidence to partners for data equality between the new Lakehouse platform and Redshift. We can show them this dashboard and we can give them a view that their data is the same. Once data products are available for partner consumption in the Lakehouse, we can optimize them for usage. In Redshift, we use distribution and sort keys. In the Lakehouse, we mirrored this with partitioning and z-ordering. During the migration, liquid clustering was announced in public preview. This gave us added flexibility to handle changing access patterns without having to rewrite huge data lakes and handling skew in data distribution seamlessly. After implementing liquid clustering, we saw pretty equivalent performance with more benefits to future extensibility and a simplified clustering keys compared to partitioning and z-ordering. Optimize and vacuum on Delta Lakes, we implemented this a long time back. We implemented Optimize as a post hook in dbt after every model run, and then vacuums were configured as separate Spark jobs to run periodically. Predictive optimization was later released, and we adopted this really quickly. We removed dbt post hooks and the external vacuum jobs. Since the optimized hooks were run after every dbt model, it included this time in the overall pipeline runtime. Predictive optimization let us decouple that, which gave us faster pipeline runtimes to meet SLAs. Both liquid clustering and predictive optimization helped benefit us by optimizing engineering time. We could remove steps that needed to be monitored, and we could allow Databricks to determine the best time to run these operations. This is one example of some learnings, how BI tools interact with Databricks compared to other databases. We found that Looker can automatically create queries with some unintended consequences. In this query here, a timestamp column, it's casted to a string. When it's executed by a Databricks SQL warehouse, it will not properly prune the files or skip data, even when that data set is liquid clustered on that timestamp column. We were able to fix this by explicitly defining the data type in LookML, which stops Looker from casting it to a string. This change gave our partner a fast query because the where condition could properly skip data when filtering on a liquid clustered data set. These kinds of issues, they're hard to discover. It makes it important to work on both internal and partner optimization end-to-end across the migration. Through this migration, we migrated more than 400 platform partners. Each partner team has their own UC catalogs provisioned with read access granted to core data products that are owned by the platform. Different teams, they use a variety of analytic and BI tools like Looker, Power BI, and ThoughtSpot. Partner teams, they have Databricks SQL warehouses provisioned for their team. That helps with resource isolation and usage-based spending. It helped create a model where the data platform can easily cross-charge for usage, and then teams take more responsibility for their usage and resource needs. BI tools, they're then connected to these team-owned SQL warehouses. This helps access and privacy be limited to that team's use case and allows for a better data governance model. The warehouses, they can be sized and scaled for availability need. For example, if we have a dashboard that's just refreshed once a week, that might only need an extra small warehouse. Or if we have consistent development in a large team, they might benefit from horizontal scaling, like 15 clusters, for example.
As you would have realized, we've gone through a journey filled with learning so far. While we're still in the process of migrating some of our platform, we've seen great results with the pipelines that have already moved over. We have successfully migrated 6 complex dbt projects, more than 70 BI dashboards, and 45 plus partner teams over to the Lakehouse environment with no missed SLAs and no drops in data quality. We leverage Databricks offerings such as streaming and DLTs to modernize our pipelines. We can now focus on gaining value from the data rather than worrying about logistics and resource contention. As a result of the migration, we achieved 30 to 40% cost savings thanks to better performance and reduced data duplication. We now have the flexibility to scale up on demand to meet urgent SLAs and don't have users stepping on each other's toes with shared compute, all resulting in happier developers. In the graph, you'll see how our Redshift costs started out pretty high, and towards the end of this migration, you'll see that the Databricks costs have evened out to a much lower level than where Redshift was, all resulting in happier managers. Now that we have migrated to the Databricks ecosystem, we're continually benefiting from it. Teams are using Genie to level up their exploratory data analyses, and having the Databricks assistant at our fingertips has meant faster prototyping and development. Getting started with RAG and LLM development is very low effort, now all within the same ecosystem. And having the Unity catalog has made data discovery much easier for new partners. Migrating up our platform to the Lakehouse has helped us gain more value from the data we host. We can now share more easily to different teams across HP and help HP make more data-driven decisions. We can scale our platform well and support more users with the same size platform team. So what's next? We're still working with some partner teams and data products to migrate into the Lakehouse. We hope to finalize this by the beginning of the next year and continue reaping the benefits of this ecosystem. Thank you for listening in on our talk today. We would like to give extra thanks to Sasha Vetter, Mike Glazier, and their team at Databricks for working with us on this migration. We hope you were all able to get some insights into what it takes to carry out a migration like this, and we would be happy to answer any questions that you may have. You can also connect with us via LinkedIn or email. Thank you.